All right, so now we are moving into the second unit. So we've been talking, the first unit was kind of introducing where we're going. Now we're going to step back away from causal loop, or away from stock and flow diagrams, the dynamical system models that we hope to eventually build, and go back to sort of where we're going to start without these so-called causal loop diagrams. And so the motivation here, this is from a story that was now seems very dated. I don't think I have a date on here, but this was a while back. I think after the first recovery from COVID-19, there was this question of, are we experiencing a so-called K-shaped recovery? So this term K-shaped comes from this idea that you had a certain performance level and some economic measures before COVID-19, and then across all sectors, there was an economic recession, and then there's a recovery. But the certain sectors, sort of the high-tech sectors that have a lot of money in them, recover very well. These are your Amazons of the world, whereas other sectors, maybe restaurant businesses, hospitality, those continue to decline. And this is a so-called K-shaped recovery. And so, if we talk about models, it's kind of, a nice thing about that. Even a letter can be a model where this K sort of describes this phenomenon here. But there are a lot of questions as to what causes these K-shaped recoveries. And so this is just from one snippet about K-shaped recoveries. And they mentioned that it could be creative destruction. It could have to do with public policy or fiscal policy, could have to do with these economic shocks. There's a bunch of different things that they list here, but then down at the end here, they say, note that these three might not be mutually exclusive. All three may play in a given K-shaped recovery along with other factors. And so in the end, this is kind of like the fishery example where we have this macroscopic measurement, like this, we can measure these things. And then we really want to kind of try to understand what are the causal drivers of all of these things. And in order for us to build models to test hypotheses about these things, we need to then be serious about and explicit and formal about what we mean by causation and causality and how to model these things. And that's what we're getting into here. So how do we evaluate the plausibility of hypothetical drivers? That's kind of what we're signed up for now. Okay, so where from last time, we talked about these dynamical systems models, stocks and flows. Stocks accumulate, but they can only change if something comes in their inflow or out their outflow. This will be something that we're going to talk about in great detail in the next unit. This is, again, just trying to anchor us so we can see where we're going. So the term stock represents the state of a system. It changes over time and reflects the cumulative impact of the system's history. How well are we, where are we today? And where are we today, of course, reflects the cumulative history of where we've been in the past. And so we refer to stocks sometimes as state variables. The rate of change of a stock it's either inflow or outflow. So we can partition things into the things that cause the stock to rise, the things that cause the stock to fall, or we can just call them flows, and they can be positive and negative. So those are some terminology we use. And whenever we see a diagram like this, if we were to draw such a diagram in a simulation tool behind the scenes, it would actually write an equation like this and solve it. So this is the big reason why this is SOS 212. It used to be called Calculus 2, because it was this idea that you learn a little bit of calculus in Calculus 1 and SOS 211, and then you build these models where these models really are just instantiations of exactly the math that you've been used to. So instead of writing formulas like this, what we're aiming to do is write diagrams like this, but really behind the scenes, we are writing formulas. We're just not using as much of the math speak. We're using this more diagrammatic speak, but these are identical, these two representations. So what we learned from last time, you can put all these stocks together into what based on what I just said, very complex mathematical expressions, which are shown as very ugly looking spider web-like diagrams. But these diagrams, my claim is, even though this looks like a mess, that this diagram is actually less messy than what it would look like if you were to write all that math out. Because again, every single stock and flow here corresponds to one of those differential equations. So this is a bunch of coupled differential equations. And this we can actually map out all these cause and effect relationships, whereas it's a little harder to see that if we just look at the expressions. And so with those webs, then we get these different trajectories, kind of like, again, the K-shaped recovery idea. We can test dynamic hypotheses here. So we can say, well, if this is how we think the world works, if we account for all the causal factors we think are important in the world, what sort of trajectories can we get out? And we can get trajectories where the global carrying capacity collapses or things kind of level off. And that kind of tells us that if we buy all of the causal factors that went into here, then we can now use this as a lens to try to understand what are the parameter differences that get us from this world to this world. And so in a world where this is possible, it's apparently also possible to, with maybe minor changes, move into this world. That's kind of the message behind this dynamical systems model. And so this whole thing is taking a term I'm going to use throughout the semester called the endogenous perspective. And so the idea here is that an asteroid didn't hit the Earth here, and that's what caused this collapse. This collapse was generated from inside the system. The call is coming from inside the house. And the idea here is that there can be deterministic relationships among all of these dynamical variables that exist within a model that lead to spontaneous changes in trajectory that we might not have expected. And so if we just were to look at these data, or just look at a K-shaped recovery, we could say, well, this clearly was caused by some external shock to the system, that something came in and things were going fine and something collapsed. But in our model, we don't model any external shocks. This actually comes out of a model where everything's humming along exactly the same way day after day, but over time, it accumulates enough changes that causes something to change inside the system. So the endogenous perspective is this idea that the observable changes in a system are a function of things internal to the system as opposed to external. Of course, there are asteroids that hit the Earth. There are external shocks. But the idea behind this particular aspect of strategic modeling is trying to say, even without those external drivers, what's possible? What could happen? And this is saying that even without asteroids hitting the Earth, you still could have these collapses that are driven entirely by predictable behaviors inside this internal model of the system. So that's the perspective we take in this class, the endogenous perspective. And that's going to mean that we're going to need to look inside systems to understand causal relationships. And feedback is going to be a major driver of our dynamics. And so last time we talked about a simple fish system like this one, where we have a state variable, how much fish are in the fishery. That state variable changes based on the regeneration rate of the fish. And we know that there's a feedback between the number of fish in the fishery and how quickly they're regenerating. And so we can zoom in on the regeneration rate, and we can say that, based on data, as the density of the fish is, if it's low density, the fish are not limited by their food. They just have to, maybe at very low density, they have to find each other. That's why there's kind of a ramp up here. So because if you're trying to model the effect that in order for fish to reproduce, maybe male fish have to find female fish, and at low density, that's hard to do. So maybe the initial growth rate is low, but once they reach some critical density, the growth rate takes off and they're basically not limited by anything. And then that's a so-called reinforcing feedback loop. More fish begets more fish. But then once they reach a critical density, then it's really hard to find food to feed all these offspring. And so now you get a negative feedback where the more fish you have, the even harder it is for the next fish to survive. And so that's a negative feedback. So all within this regeneration rate graph, then we're able to capture these two types of feedback loops, reinforcing and balancing, that are somehow acting together. And they act together in this type here we're going to call S-shaped growth, that we're going to talk a lot more about when we hit to like chapter 5, when we start really getting into these models. But the basic idea here is if we can identify these causal relationships inside systems, then we can start to predict patterns and test those predictions out. So we would predict If you combine a reinforcing feedback loop with a balancing feedback loop, you would get initial slow growth, then fast growth, and then it would taper off. And certainly if we then simulate this system, we see that the fish stock, line 2 here, has slow growth and then tapers off after a period of fast growth, exactly as we might expect. So this is going to show us that there's a consistency. And when we have reinforcing feedback loops followed by balancing feedback loops, we get S-shaped growth. Again, the endogenous perspective is that this tapering off isn't because there's some external hand that comes in and says, no more fish. The hand is inside the system. The system itself decides on its own when there are too many fish and it levels off. That's the endogenous perspective. And so if we understand the causal relationships inside a system, we can start predicting these type of phenomena and maybe acting to move them in directions that make sense for sustainability. So so feedbacks. The trouble with the diagram like this is that the diagram itself doesn't really tell a story of two feedbacks. I had to go into this cryptic net regeneration loop or a variable here, and I had to see what that graph looked like. And so it would really be nice if we had an alternative way to draw this diagram that would make these two feedbacks, simultaneous feedbacks, obvious. And it turns out that we'll learn that there is a way to do that. I could have drawn the same system this way, where I have my fish population in the middle, and I have inflows represented by births and outflows represented by deaths. So rather than having a single net regeneration flow, I have an inflow and an outflow, explicitly modeling these two separate processes of birth and death. And when I separate these things out, I still may have to put all of the density dependency that I had in here, but by separating them out, in some ways I create more work because now I have to model that density dependency in two places. But it makes the causal relationships more clear. I can see now that there is a positive feedback relationship between population and birth. The more population I have, the more births I have, the more births I have, the more population. And I can see there is a negative or balancing relationship on the back end of that. So the more population I have, the more deaths, just because there's a certain death rate per individual. So more individuals, more deaths. The more deaths I have, the lower the population. So right now, I've actually now visualized both feedback loops simultaneously without having to analyze the shape of some curve. And so this is, I think, even more appealing of a view of this system. And so what we're going to be talking about here is we're not yet ready to build these stock and flow diagrams yet. But what we can do is start to build these causal loop diagrams, which don't have the quantitative part in. They don't have the rates explicitly modeled. So we can't simulate these and generate these curves, but they capture all the causal relationships. So I still can say there is a birth rate. I can't put it in, but there is a birth rate. It affects births. The births affect population. The population affects deaths. Death affects population, and so on. I can say all of these things that I can say up here without ever actually having to specify that, well, okay, but the birth rate is exactly one fish, one offspring per fish per year or something like that. I don't have to specify those numbers just yet. And so this is kind of intermediate where this level here, where it doesn't have all the dynamical details, still lets me see these feedbacks. So this is what we are now learning how to draw, these causal loop diagrams. And when we learn how to draw these causal loop diagrams, we just look for the causes in a system, they're in these internal networks. It will help us eventually build these stock and flow diagrams because we'll be able to come up with all of these things and then be able to say, well, then how do we make it dynamical? Well, we need to add in the stocks and flows, and where are the stocks and where are the flows? And we can start with this and build up from there. So that reflects kind of the way Moorcroft does things is we can translate mental models using this process where we have in our mental model that there are certain causal relationships. We're going to take it out of our mental model, draw it out as a causal loop diagram. Once we've got all the causes that we think matter, then translate that into a dynamical model we can simulate. That's one way to do this process. There's an alternative way that some people like better, where you actually start with the dynamics here. And so in theory, I could have flipped this classroom around and just jumped straight in to these dynamical models, tried to relate them to SOS 211. So turned calculus into these models, got them simulating. And then once they were simulating, then we could have analyzed them and say, can we make sense of these patterns we're seeing? Oh, look, there's a negative feedback there, there's a positive feedback there, and so on. So that's the other direction, is start at the stock and flow and then make sense of the stock and flow using the CLDs. Those are both fine ways to do things. Our book goes CLD first, and that's the way I'm going to go in this class. There's another popular book used for studying dynamical systems and sustainability by Andy Ford, Modeling the Environment, and he goes the other way, where he does stocks and flows first, and then CLD is towards the back of the book. So in the end, when you go out and do the stuff in practice, you do both all the time. So just for educational reasons, we have to pick a direction, and that's the direction we picked. But I know that some of you are going to feel like the stock and flow first appeals more to you, and I get that, but I had to choose a direction. And so I just went with that, because actually this textbook was easier to get a free copy in the library. And so I said, we'll just go with the Moorcroft textbook and the approach they take. So that's why we're doing CLDs first. But in theory, you could do the other direction as well. All right, so that's kind of where we're going. So today we're going to start introducing CLDs, how to draw them, where to see them, how to analyze them, and so on. Any questions or comments on that so far, including online? Let's take a look at the chat. All right, pretty clear. Okay. All right, so some terminology that we got to learn here. We've got negative feedback and positive feedback, basically, but there's a bunch of different names for these two things. So whenever I refer to positive feedback, I might also just use the word reinforcing feedback. They're identical, it's the same thing. Might also refer to it as a snowball effect. Exactly the same thing, just a different name for it. Maybe in some context, it makes better sense to say that. The other names you hear people use are vicious and virtuous cycle. These are both positive feedbacks. And that's a little confusing because vicious sounds like a negative term. And so the point here is that the phenomenon is a phenomenon of growth. And so any phenomena of growth, which is why they're sometimes shown in a diagram with this little growing indicator over here, any phenomenon of growth, we're going to call a positive feedback or a reinforcing feedback. Now, sometimes growth is bad and sometimes growth is good. If, for example, let's say that you have an unhealthy weight and it makes you feel upset that you have an unhealthy weight, but that triggers an emotional response that makes you eat. And then that generates maybe a weight that is not in the direction that you would like it to go in. That's an example of it is a positive feedback, but it is a vicious cycle. Compare that to a virtuous cycle where maybe you find that if you get up earlier in the morning, you get more done in the day. That makes you happier and less stressed out at the end of the night. So you go to bed earlier and you're able to get up even earlier in the morning and get even more done, which makes you even happier and more relaxed at the end of the night, and so on. That's also a positive feedback, but we refer to that as a virtuous cycle. So the valence on the cycle can be communicated by vicious or virtuous, but they're both positive feedbacks. On the other side of the negative feedback, then, negative feedbacks aren't always bad. So a negative feedback is the opposite of that. We'll use the terms negative feedback, we'll use the term balancing feedback, and the term counteracting feedback. And so sometimes you'll see it'll be annotated C. The C stands for counteracting. And this is about feedback that brings things into balance. And so balance can be a good thing. So your body has a homeostatic process that keeps its temperature at roughly 98.6 degrees Fahrenheit internally. If you get a little warmer than that, processes are triggered in your body that brings them back to 98.6. If you get colder, other processes are triggered to bring it back up to 98.6. It keeps your body in balance at 98.6 degrees, and that has a lot of good things about it. So that's an example of a negative feedback that is good. There can also be negative feedbacks that are bad. So you can be trying to enact social change, and every time you push against a system trying to make the system change, it pushes even harder back against you and just brings things back to the status quo. And so that's an example of a negative feedback that's regulating maybe a negative status quo. So just the terms negative and positive themselves do not indicate good or bad. They just indicate, is it a growth process or a balancing process? So that's the kind of the terms you hear. So the symbols we'll use, usually like a plus is the common one I'll use. Some people actually draw a snowball. A lot of times, because these are in feedback loops, they'll be circled by directions telling you where the feedback loop is going. Some, again, people draw actually a little growth curve right in the middle of it. On the negative side of things, again, there's negative feedback. Sometimes people draw a little scale indicating a counteracting or a balancing feedback. Sometimes they draw a little system kind of with this exponential decay where it's coming down to some asymptote. And all of these things are ways that people annotate that you're looking at this type of feedback. Okay, so any questions about these terms? I haven't described to you how to find these negative feedback. That's coming. So when we look at causal loop diagrams, there's a recipe for how you tell if it's a negative or a positive feedback, and we're going to get to that. But just generally about the terms in, here, I want to make sure that we're pretty clear. Okay. All right, so before we can actually analyze the feedback loops, we have to look at the individual links. And so the arrows are links in a causal loop diagram. I'm going to have two variables in a causal loop diagram, A and B, and I might want to indicate that there is a positive link, a positive causal link between A and B. So the idea behind positive here is that an increase in A causes an increase in B. Or the flip side of that, a decrease in A causes a decrease in B. This is some reason why some authors don't use a plus here, they use an S for same. And some authors don't use a minus here, they use an O for opposite. So positive feedback is one where if the system's just kind of sitting, hanging out and just resting, then both A and B are sitting where they are. But if you perturb A to make A larger, then a little bit later, B is going to be larger. If you perturb A to make A a little smaller, a little bit later, B is going to be a little bit smaller. So that's what I mean by a positive feedback. They move in the same direction. I'm sorry, I didn't mean to say feedback, positive causal relationship. So this causal link is positive, they move in the same direction. Down here, the negative causal link is the flip of that. So a little perturbation in X that makes X larger is going to make Y smaller. A little perturbation that makes X smaller is going to make Y larger. So if you were to think about the temperature in the room and your happiness, so you could say, well, there's temperature in the room and there's happiness. And you'd say, well, the temperature of the room goes up, my happiness maybe goes down if it's hot in this case. So in that case, would that be a positive or a negative relationship? If the temperature of the room goes up and my happiness goes down, is that a positive or a negative relationship? I hear, how many people say positive? And online, you can feel free to voice too. How many people say negative? About negative. Yeah, I would describe it as negative as well. So that's what we're kind of saying here. All right, questions about this, about positive and negative links? Again, these variables here are kind of arbitrary variables that we say are in the system, things we can point out in a system, things that potentially could change over time. Again, like temperature, like mood. We're going to learn rules for how to pick these variables as well. Okay. All right, so, and I just want to, I kind of hinted at this earlier, this is all relative to a no change baseline. And so, you kind of have to, it's not about whether A is a negative number. It really is, if I let the system go, and then as I'm leaving it go, and then I just perturb A up or down, I don't actually care if A is negative, but I want to know how does it change. So if the change in A is positive, then what is the change in B? So this is all relative to if things are cruising along and you didn't perturb anything. That's how we decide these pluses and negatives. All right, so if we've got a bunch of these arrows all coming into one, this is where it can get very confusing as to how to choose these arrows. And something we have to remember is that we are going to hold all of the other variables constant, even if that's impossible to do in the real world. What do I mean by that? So I've got a relationship here saying there's some variable X, And it is related to B and A and C. So A, B, and C all have some causal interaction with X. And so if I increase A, it's going to increase X. If I increase B, it's going to decrease X. And the question is, what happens if I increase, what is the relationship between C and X? Now, it may be that there is some relationship between C and other variables in the system. So it might be that it is impossible to increase C without also increasing A. We have to forget about that. We have to say, imagine a hypothetical world where you could keep A and B the same, constant. And if you manage to only increase C, what would happen just due to that change in C with X there? So it's kind of like, you know, if there could be a bunch of different, again, if we go back to happiness or something like that, if your happiness is the X, you know, there could be a bunch of things. There could be a factor that if you got more money in your bank account, that might increase your happiness. But if you got more homework, that might decrease your happiness. And then this one down here would be if you took more classes. Now, you know, if you take more classes, you're probably also going to get more homework. But we have to sort of think about, like, imagine if your homework didn't change, but you just managed to add in classes or something like that. Then that you have to say, well, what would be the effect just of the classes alone, not on the homework? Now you say, but in reality, you know, if I add classes, I'm going to add homework. Well, if I draw the whole diagram, that relationship between classes and homework will be represented there, but it'll be represented separately. So I'm looking for the direct relationship between the number of classes you take and your happiness, not the indirect relationship that classes have on homework and how homework has on happiness. So we're only showing direct relationships. And so as we do more examples of this, I think this will become more clear, but just want to drive this home. We want to hold all of the other things constant. So we only consider the effect on X of increasing only C. Any questions on that? Does that, and maybe this will, again, make more sense as we do another example here. The other notational thing on these arrows are these two little lines. They're supposed to look like a capacitor in electronics, or just a box that says delay. It's identical. And this indicates that there is a causal relationship between these two, but there is an appreciable delay in how quickly the relationship acts. So if I think about in a shower, the flow of hot water versus the temperature of that water, if you crank up the flow of hot water on a shower spigot, then there might be a huge delay as to when the water temperature actually gets hotter. Or the other way around, if you crank it down, there might be a huge delay in how the water temperature changes. So strictly speaking, there is a positive relationship. I crank up the flow, the temperature increases. I crank down the flow, temperature decreases. But on a small time scale, if I crank up the flow, if it takes 3 seconds for me to notice, then that might cause me as a decision maker to crank it the other way because I didn't think there was a change. So delays really can be really important to our decision makers. Now, you might say, well, there's always going to be a delay. It's physics. And that's true, but not all delays are appreciable. Some of them are negligible. So, you know, when I turn my steering wheel, really my tires turn pretty much immediately. But when I step on the throttle of my car, it doesn't accelerate immediately. So if I was modeling those two things in my car, I probably wouldn't bother modeling the delay between the steering wheel and the tires, but I would model the delay between the throttle and maybe my speed. And so me as a decision maker, the delay between the throttle and the speed really matters, whereas the delay between the steering wheel and the tires doesn't matter. Now, you can always just put delays in because you're not sure. But then when you actually end up getting to the dynamics of the thing, and you actually start parameterizing these things, and you find out that, like, there's so many other delays in the system that are so large that your system becomes completely insensitive to the small delays, and then you can just pull them out. So sometimes we have to wait until we get to the dynamical systems model and do what we call a sensitivity analysis to figure out when we can just remove a delay, because changing, you know, if it's a microsecond delay versus a 10 microsecond delay, it doesn't really matter because there's like hour-long delays in the system. So in that case, if I change my system from microsecond to 10 microsecond and run my sim looks identical to it did before I made the change. So in that case, maybe I can just get rid of the delay. So exactly when to take the delay out, this is going to be something that's going to take practice at. I would say don't draw a delay by default. Draw without a delay by default. And then when you finally reach a system where, like this is one where the delay clearly is like salient. You feel that delay, then put that in to indicate that this must be a really important special feature of this system. Okay. All right, so questions about delays. All right, so now loops. So we've almost have all of the elements that we need to draw these causal loop diagrams and analyze them. So when we put causal loop diagrams together, we might have a loop. I should emphasize that a causal loop diagram, a CLD, it's not called a causal loop diagram because it always has a loop. It's called a causal loop diagram because it helps us find loops. Not all causal loop diagrams have loops. So when we see something that looks like a loop, we have to see, is it really a loop? And then once we see that it is a loop, then we want to ask, is it a negative feedback or a positive feedback? And the way we do that is we find our loop, and we're going to start at one node. And I think I'm going to unwrap this in the next slide here. Let me just see here. Okay, well, we'll see this in a second. So what I'm going to basically do is start at any one node. It doesn't matter where I start. And I'm going to walk around the loop until I reach that same node again. And I'm going to count the number of negative links that I walk across as I go all the way around and stop back where I start. So if I go around and there's an odd number of negative links, then it's a negative feedback loop. If I go around and it's an even number of negative links, then it's a positive feedback loop. So I've got an example negative feedback here, an example positive feedback here. So this negative feedback only has one negative. Notice that this positive feedback has two negatives. So it's like the second negative undoes the first negative, turning it into a positive feedback loop. So usually once we've identified a negative feedback loop, we label it using one of those symbols from that diagram we started with here. I'm using this symbol here, which shows that the clockwise loop is negative and this clockwise loop is positive. Now, why counting? Well, if I unwrap this thing, so I'm going to start at A, and I just unwrapped it. So I've got an A on both sides here. So there's an A on the left, and then that exact same A on the right. Then by unwrapping this loop and counting the number of links, then what I see here is if I kind of think of the direction of the changes, if I get a little positive change in X, I will get a positive change in A. I'll get a positive change in B. If I get a positive change in B, I'll get a positive change in C. But here, because there's a negative relationship, if I get a positive change in C, I'll get the opposite negative change in A. So it's like multiplying ones across there. So this positive link is like taking whatever the change is currently and multiplying it by a positive one. So if I do a negative change, if I multiply that by a positive one, it's still a negative change. Go to this, it's still a negative change. But at the instant I hit a negative one, a negative change times a negative one becomes a positive change. So we can kind of model the interaction of links as multiplications of pluses and negatives, and it works just the same. And because the end-to-end influence, is the product of signs, then that tells us that if we have an even number of negative links, all those negative ones are going to cancel out. Because if you have a string of negative ones, it only matters whether it's an even numbered string or an odd numbered string. So if there's an even number of negative ones, they'll end up becoming the effect of the positive. The other way to look at that is if I'm really just focusing on the relationship of A back on itself, if these were two negatives, like a negative here, so I should do this with a pointer, if there was a negative that was, if this positive link here was negative, as well as this one negative here, then that would indicate that even though A causes B to go up, and then the upwards movement of B is going to cause C to go down, because C is negatively related to A, C's decline is just going to cause a greater incline or increase in A. So the two negatives kind of cancel each other out. So there are questions about this, the way we label these loops. Does that make sense? Okay. You just count the links. Yeah.
So it's always going, so it says even number
Great question. So the sorry, I think I ate something on the way over, and it's stuck. So the question was, is it only the negative links? Like, why aren't we counting the positive links? Do we only count the negative links? Is that sort of a good summary of what you're saying here? Yeah. So and that's only the negative links matter. The positive links, because the positive links kind of carry on whatever the change was before them, it's as if they're not there. So we only have to count the negative links. So the polarity of a feedback loop is just the number of negative links in it. Any other questions? I see online. So online, there was a question of, could be a real world example. And so a real world example could be this, if I'm thinking about, I'll go back to a car example. Like, imagine I'm trying to control my speed, and I look down, I would like to control my speed at 60 miles per hour. And if I see that I'm below 60 miles per hour, so I'm at 55 miles per hour, then that's going to make me push on the accelerator, which is going to cause my speed to increase. But as my speed increases, the 55 gets closer to 60, that's going to cause me to start taking my foot off the accelerator because there's not as much of a difference there. So if I were to model those things, if I can see if this will be ugly here. I'm going to try to do a little trackpad drawing here. So if I were to model my speed and my throttle, so there's a relationship where, in this case, where again, keep in mind that my speed is underneath my target speed, then the idea here is that if my current speed increases, my throttle is going to decrease because I'm going to get closer to my target. Maybe I need another step here. Let me try to think of it as more of a third example here where I've got, so my speed increases and, let me try to think of a positive feedback example that would maybe be better. So here, if I'm going to continue this one since I started it, so the idea here is if my speed increases, my throttle is going to decrease. But if my throttle were to increase, my speed would increase. And so here I've got a negative feedback loop. Now, if let's say my car was broken and pushing down on the throttle actually did the opposite thing. So pushing down on the throttle actually caused my speed to decrease, and lifting up on the throttle, the pedal, caused my speed to increase. Then these would be two negatives here. And the idea here is that my increase in speed might cause a decrease in throttle, but the decrease in throttle would then cause a further increase in speed. So I would get the negative action of speed on throttle gets undone by the negative action on my broken throttle on speed. So I hope that's sort of it. What we'll do, we're going to label a bunch of these diagrams in a second, and I think that that'll help. And it looks like online there was confirmation there. So any other questions about this link labeling? Okay. So the other thing that we'll do is once we've labeled the links and labeled the feedbacks, then we don't have to do this, but you'll often see this in Moorcroft. Every time we find one of these feedback loops, a lot of times we also just add an annotation to help us name that feedback loop. So I've got this example here, maybe I'll use the pointer, where this is hunger and amount eaten. And so kind of like the throttle and speed example, it's a balancing feedback loop. or a counteracting feedback loop. The more hungry I am, the more I eat, the more I eat, the more I choke. But the more I eat, eventually, that's the delay there, the less hungry I feel. So this is the balancing feedback loop. So I labeled it as a balancing feedback loop, great. And then I just added a little annotation in the middle to say this control of food intake. That annotation that you're gonna see in the Moorcroft textbook isn't a variable or anything like that. It's just meant to be a comment to point out that that's what this loop is. Because what we're hopefully gonna see is in these complicated causal loop diagrams, once we label them all, we're gonna step back and only look at the feedback loops. We're gonna stop looking at the variables. And that's why we just label these loops. So there's other examples here. This is the shower example where I've got a flow of cold water, I've got a desired temperature, I've got the process of actually trying to regulate the temperature by turning the water on and off, sets up one of these balancing feedbacks. I kind of step back and I just call this the comfort seeking loop. And then here we've got a crime spiral. So this is a nice example. Actually online, they said, can you have an example of one where we see these two negatives kind of cancel each other out? And we'll see this in chapter 2. But the idea here, imagine these are drugs. So we've got a price of drugs. If the price of drugs goes up, we're going to see drug-related crime go up. And as drug-related crime goes up, we're going to see more pressure for police. As there's more pressure for police, we're going to see more police on the streets and more drug seizures. But with the increase in capturing of drugs, so you're taking drugs off the street, that's going to decrease supply. So the increase in this one is going to cause a decrease in that one. But decreasing supply, what does that do? The positive effect, if you want to call it that, of decreasing supply is going to have the negative effect of increasing drug price, which is going to cause a positive feedback here. So individually, it looks like taking drugs off the street is going to do a good thing because that reduces the supply of drugs. But if we look at the system, reducing the supply of drugs by itself is not going to do anything to solve the problem that price is driving this whole thing. In fact, taking drugs off the street is going to just increase the price of drugs. And so any benefit you got from decreasing this thing is going to get counteracted by the increase in price. And this whole thing is going to spiral in a vicious cycle that's a reinforcing feedback loop. And that's these two negative loops undoing their effect, canceling each other out. So any questions about that? Yeah.
So as these loops get bigger, more complicated, why don't they put like negative or positive in the middle to indicate it's like a negative or positive feedback?
Great question. So the question is why didn't they put like a negative or positive in the middle here to indicate this was a negative feedback? That's what that R is supposed to be. So that's one of the ways they do that. So R is reinforcing. So different authors are going to do different conventions. Moorcroft uses B for negative, that's balancing, and R for positive, that's reinforcing. Other authors use a plus and a minus. So other authors use C for counteracting in this case. So it's just going to vary. We just have to get used to seeing those. Great question. Any other questions? Okay. All right, any other question? Okay, no. All right, so let's see more examples. So home heating system, a nice coupled feedback system here. So we've got air temperature is a really important thing in our home heating system. So on the outside side of home heating, then as the air temperature inside the house increases, then the amount of heat lost to the outside, this is in a place that has real winters. And so as air temperature inside the house increases, if it's hotter than outside, then the loss in heat, in this case measured in British thermal units, but just heat loss increases. And if your heat loss increases, then the energy content inside the house decreases. And if the energy inside the house decreases, then that, because of this positive here, is going to mean that the decrease in the energy inside the house is going to lead to a decrease in air temperature. So this loop on the right-hand side, the outside loop, is a negative feedback loop because I only see one negative link up here. Now, if I look on the inside loop, what's going on inside the house, then I've got, as the air temperature gets, let's say it gets colder, then there is an opposite relationship where the furnace heat will increase. So as this decreases, the furnace heat production is going to increase. And the furnace heat production, as it increases, it's going to increase the energy content inside the house. And as the energy content inside the house increases, as we already said, the air temperature increases. So here's another negative feedback loop because it only has one negative link. Notice that these external links here, the thermostat's target temperature and the outdoor temperature, don't play a role in the feedback loop. We don't care about them whatsoever. They're important. I mean, if I increase my thermostat's target temperature, it will increase the furnace heat production, which will ultimately change the air temperature inside the house. But in terms of the feedback loop, they don't play a role in the feedback. So we don't worry about them as we're counting the links. So we get two negative feedbacks coupled together. So any questions about that? To clear how we labeled the links and then how those links added up to these feedback loops. Questions online? Okay, great. All right, now, here's another very similar example, but in some ways is a little trickier because we've got the double negatives going on. So, and triple negatives even. So here, an automobile market. So very similar setup here, but we're gonna say, we'll start at the inventory cars at dealerships. So there's cars at dealerships. If you increase the inventory of the cars at dealerships, with the extra supply, then the market price is going to decrease. And so we get this vertical line here is negative here. Now, if the market price increase, or sorry, if the market price, well, it doesn't matter which way I do this. If the market price increases, then the amount of cars that are produced is going to increase as well. Now, I said, notice how I said that here. If the inventory increases, market price will decrease. But then I flipped and said, if the market price increases, car production will increase. Notice that when we choose a link, it's tempting to continue a story, but I don't like to continue a story because I make mistakes. And so I like to always reset and say, all right, if I could have said if the inventory increases, market decreases. If the market decreases, car production decreases. But in my head, because I might accidentally mark this as a negative because I just said decrease here. Like I just have this heuristic in my head that I like to make the thing on the leading edge of the arrow, like on the tail end of the arrow, I like to make that thing increase and then ask what happens to the head. And so if the head ends up increasing, I put a plus. If the head ends up decreasing, I put a minus. So if the inventory increases, market's going to decrease, that's a minus. So then I reset, I forget that I said that at all and say, well, what happens if the market price increases? The market price increases, I know car production is going to increase. That's why it gets a plus there. Reset, if the car production increases, what's going to happen to the inventory? Well, the inventory is going to increase. So this production loop on the left here tells me that eventually we're going to stop car production and there's just going to be an inventory that's out there because as you get more and more inventory, you get ultimately will produce less and less cars until you stabilize at some inventory. Now, what happens on the market side of it, on the purchasing side of it? Well, as the market price increases, fewer people are going to buy cars. So the increase leads to a decrease, and that's why that's a minus. Reset the logic. If the retail car sales increase, what's going to happen to the inventory of the cars at dealerships? Well, if the sales increase, people are buying more cars, the inventory is going to decrease. And that's what makes that a minus. So I get these two minuses here. So now I have three minuses along this side here. It's an odd number. So this here is a negative feedback loop. So these two things are both trying to regulate the number of cars. They may not be trying to regulate it to the same level. The same thing back here. You could argue that the outside loop is trying to make your house freezing cold. The inside loop is trying to make your house, whatever, 70 degrees Fahrenheit. So they're both trying to regulate, but they're going to fight against each other. Likewise here, you could argue that the market is trying to push more cars out, or sorry, the production team maybe is trying to push more cars out, but maybe on the sales side, they're not looking forward to buying a whole lot of cars. So these two things don't necessarily are in agreement about their set points, but they're two negative feedback loops interact. So these two things together have this shared quality of being a balancing loop next to a balancing loop with a stable quantity like air temperature or inventory in between them. And so that ends up creating this interesting property where you've got a perpetually unmet goal on both sides. So if you think about that, what really is happening in your house is you would like to set the air temperature to 70 degrees Fahrenheit, and it gets there, but then the temperature, but then your thermostat or your furnace turns off, and then it gets colder. So you're constantly turning on the furnace just to keep things close to 70 degrees. Likewise, you never actually reach all the way down to 0 degrees. So it's like the outside is trying to make your inside like the outside, and it never quite gets there. So you constantly have perpetually unmet goals, but nevertheless, they come to some balance point at this stable quantity here. And so this idea of having a perpetually unmet goal on one side, perpetually, so if I go back to that, even though these are two balancing loops, if I kind of zoom in on one of these perpetually unmet goals, wrong direction, sorry. If I zoom in on one of these perpetually unmet goals, this particular archetype, when you have two balancing linked by a stable, has this weird figure eight property where the kind of canceling out happens across two loops, where it's like I've got a negative feedback, but then figure eights along another negative feedback. And then ultimately the figure eight sign is positive. It's like I get a reinforcing feedback here. So these two loops together, it's like they reinforce growth in this thing out here. Likewise, they reinforce growth in this thing over here. And so when we see these two things, a balancing loop next to a balancing loop with a stable quantity in between, we refer to this archetype as escalation. This is so-called escalation behavior. And it's like another level. Like I had negative feedback. Well, now I'm talking about naming groups of loops together. And we can name these, in this case, escalation. And just like a negative feedback's not always bad, and a positive feedback's not always good, escalation is sometimes bad and sometimes good. Escalation in the temperature example is a bad effect because it means there's constantly waste in trying to keep the house out of equilibrium. But in the good, it's an economic engine on the other side. So in this case, we're constantly generating sales and GDP, and I guess depends on how you view that, but this is sort of driving a market where this is sort of driving waste. So, but it's the same dynamical process in both cases. And so that's one of the things we can do with these causal loop diagrams is start bubbling up to groups of loops together and looking for these common patterns. Okay, so questions about this. So I'm not asking you to memorize escalation just quite yet. We're going to get to a point in, I think, Unit 3, where we're going to look at, and it's going to, if you've taken some SOS 220, you're going to see a lot of repeats that you've seen from there, limits to growth type things. So we're going to start naming these types of things. This is just kind of a preview into what's going on there, what we can do when we have these loops together. All right, so any questions about this? Questions online? All right. Okay, so let's do a sort of a classroom example here. So I've got simple system. I got 3 question marks I want us to label. So I got chickens on this side and eggs on this side, kind of a play on the classic kind of puzzle here. So so let's think, how does eggs relate to chickens? And so we know this is either a plus or a minus. How many people think this one should be a positive, a plus? See a lot of hands. Online, if you want to say a positive or negative, how many people think this should be a negative? Okay, I don't think I see anybody. Let me see online. I see positive. All right, and that's what I would say. I would say that one should be positive. So let me go and mark it. because with the more eggs I get, eventually, the more chickens. So if I wanted to, I could probably put a little delay symbol here just to be complete. All right, so what about this one, this up here? So how many people think this question mark up here should be a positive? All right, a lot of hands in the room. How many people think it should be a negative? All right, likewise, I would say, and positive I got online as well, I would also put that as a positive. Because again, there might be a delay here, but the idea here is if I get more chickens, eventually I'll get more eggs. So now I look at this and I count and there is 0 negative links. So if there's 0 negative links, then I have to think, well, what is this, the polarity of this? How many people think this is a positive feedback loop? How many people think it's a negative feedback loop? Online, I see positive there too. And that's what I would say, this is a positive feedback loop. I might also label it as a reinforcing feedback loop. And I'm sure I'm forgetting some of the other things we could call it, but those are kind of the two big ones, a positive or a reinforcing feedback loop. I could put either of those in that label there. So it's kind of a simple example. Any questions on this? All right. Now a little more, so now we've got all the links labeled. So now I want to label all of the loops. And there's a claim here that there are 3 loops. So when I look at this, I might initially want to label this inside piece here. But if I look at this inside piece, it's not actually a loop. If I go from A2 to B1, I can't go anywhere inside this inside loop here. So I can go A2 to A3, but then I can't go anywhere here. So there is no loop in the middle here, but there are 3 loops. So, so let's see, well, there's definitely one loop over here. So it goes from A2 to A3, that's a plus. A3 to A1 is a minus. A1 to A2, that's a plus. So if I look at that, I count those up and it's got 1 negative link in that loop. So how many people would say that's a positive feedback loop? How many people would say that's a negative feedback loop? I see a lot of hands for negative. I would go for negative as well. So I might do a little negative and I might draw a little symbol indicating that the loop, there is a nearby loop going clockwise that I'm calling negative. Go over on the other side here, a second loop. This is definitely a loop, B3 to B1, B1 to B2, and then B2 to B3. So here I see B3 to B1 is a plus, B1 to B2 is a plus, B2 to B3, that is a negative. So again, I have 1 negative feedback loop. So it's identical to the other case. So I'm going to also label that as a negative. All right, where's the third loop? Anybody see it? Yeah.
It's on the alphabet, A2, B1, B1, B2, B3.
All right, that's great. So yeah, it's all the way around the outside is the third loop. So you only have to look for all of the loops here. Now, fortunately, tools like Vinsim and Insight Maker, they actually have tools inside where they'll go and find all the loops for you. So in case you miss one, but we have to kind of learn how to do it, you know, to walk before we can run. And online, somebody also pointed out that large loop there. So if I look around the outside loop, I got A2 to B1, I see a positive, positive, negative. So that's 1 negative, positive, another negative, that's 2 negatives, positive, and I think I started with A2. So I counted 2 negatives. So that tells me that this long loop is a positive feedback loop. And I am going to draw it, since it's going this direction, I can also draw it with a loop going around here. And I'm just trusting that the reader is fluent enough with causal loop diagrams that they'll know that I'm not referring to this inside space as the loop, that they'll know that they need to look for a clockwise loop that is, and you know, they'll see this one isn't a clockwise loop. So where is the other one? And it's around that other side there. So sometimes there's a little bit of squinting that goes on when you look at these causal loop diagrams. So any questions about this one? Okay. All right, so now let's do the flip side of this. These are all labeled, but they're wrong for some reason. So, so if we look at this one here, So I'll say this one here, I'll point with the pointer. If I look at the top left one here, what's wrong with this diagram and how it's labeled? Assuming all the links are right. Yeah.
It's labeled as a positive feedback loop, but it should be negative.
All right, so it says labeled as a positive feedback, should be negative. Online, I got the same answer, should be a negative feedback loop. And that's correct. I would say that this here is the wrong polarity. It should be a negative feedback loop. And why should it be a negative feedback loop? Do you want to explain?
There's one negative.
There's one negative from C to B. So there's only one negative loop, so there has to be a negative there. All right, so over here, what's the problem with this one? Yeah, not a loop, right? So this one here, and that's an online, we've got the same answer, not a loop, because C has no input, and I think that's a great way to say it. So this is, I would just erase this, but it's still a causal loop diagram. Causal loop diagrams don't have to have loops. They are tools to help us find loops, but they themselves don't always have to have loops. So this is still a causal loop diagram. It's just improperly labeled to have a loop there. So it's a causal loop diagram with no loops. All right, any questions about that? All right, so I would say, I'm not gonna do this one, but I'd encourage you to think about, if you're looking for more practice of this, this is a nice example, the squirrel, or the bird feeder example that I started with in first class, might be an interesting one to go through and say, let's find all the loops. And because there are a lot of loops in this one. And so he has labeled red as a negative link and blue as a positive link. And he's actually put words on them like adds to, creates. So there's a little bit of an ontology feel here. But you can kind of tell like helps deal with, that's like a negative. So all the ones that are red are negative, all the ones that are blue are positive. And so if you're looking for an extra exercise, it's totally optional. This is a nice try at home example to try to find all the loops and label them in that one. All right, so any questions about this process? There's only one other small detail that I want to go over today, which involves how we name the links or how we name the nodes. Okay. All right, so constructing these diagrams. So the one thing is when we're picking the things to put in the diagrams, this is the major trap. We really want to make sure we don't accidentally mistake causation and correlation. So an example of that is if it's hot outside, we know that that can cause ice cream to melt. If it's hot outside, Phoenix sun, people can also get sunburn. Now, if we aren't thinking about the sun, we might notice that you get a lot more melted ice cream, or not even melted ice cream, just ice cream use. A lot of people eat ice cream when it's hot out. A lot of people get sunburn when it's hot out. If you forget the sun, then you might be tempted to say these are causally related, where if you eat more ice cream, you get more sunburn, or you get more sunburn and you eat more ice cream. There might actually be a relationship that people with sunburn want to eat more ice cream, but it's, and that would be something we'd want to model, but the main effect here, this is purely correlational. So with that in mind, this would be the wrong causal loop diagram. So technically the arrow is in the right direction. It is the case that ice cream sales go up at the same time sunburn goes up, but they're not causally related. Sunburn isn't going up because ice cream is going up. So you say, well, how do I always know that this isn't causally related? Well, again, these are forming dynamic hypotheses. And so I would, if you drew that, I would ask you, are you really hypothesizing? Is it your hypothesis that there is a causal relationship between ice cream sales and sunburn rate? Just because you looked at the data and saw those are correlated together. And that might be your hypothesis, but most likely you're just responding incorrectly to the data that you saw. A better hypothesis is that the average temperature is the variable that you missed, and you need to include average temperature and both of those. And average temperature doesn't have any inputs coming into it, but as it goes up, both of these happen to increase, and they're not related whatsoever. Now, I could maybe draw another line, like maybe there really is a case that people with sunburn like more ice cream, so maybe sunburn rate is positively related to ice cream sales as well. So maybe that's there, but it's not like that's a feedback or anything. That's just, that is a separate thing. the relationship that the main relationship between the ice cream sales and sunburn rate is due to average temperature. Okay, does that make sense? Correlation, causation. Want to make sure you don't draw correlation diagrams. You're drawing causal diagrams. Okay, and then other things is names. And we'll talk a little bit more about this when we get to Moorcroft's chapter on CLDs, but variables must be nouns or noun phrases. You don't want to make them verbs. There should be no verbs in the things here. So like, for example, an incorrect example here, I say costs rise is positively related, has a positive causal relationship with price rises. Well, this is a little weird to me because like I want the verb to be in the link. And now I've got verbs at both sides of the link. And I don't know what to do with that. Like, what does it mean for costs rise to rise? What does it mean for prices rises to fall? Like, I don't know how to deal with it. What I really needed was this over here, costs and price. That makes total sense to me. As costs rise, what happens to prices? They also rise. Oh, good. So there's a plus link between them. So nouns or noun phrases is what you want in your diagrams. The other thing is you want a clear sense of direction. So feedback from boss, positive mental attitude, or has a positive relationship to mental attitude. In your mind, your mental model probably was more descriptive than feedback from boss. For me, reading that as a stakeholder, trying to understand your diagram, I don't know what type of feedback there was. Was it positive feedback from your boss? Was it negative feedback? Are you really the type of person that regardless of what feedback you get, it increases your mental attitude? That's probably not what you were trying to model. What you're probably trying to model is something like, oh, when I get praise from the boss, that increases my morale. That's the other thing, mental attitude. What does it mean for mental attitude to go up or down? Like attitude could be like a bad thing, or it could be a good thing. So let's just be explicit. As I get more praise, my morale increases. So it's a little bit clear there. There's a clear sense of direction. The last thing here is that their normal sense of direction should be positive. So when you have a choice, try to make it positive. So losses based on these two rules is totally reasonable. But as costs increase, saying that my losses increase just seems like a double negative. What probably would have been better is saying as costs increase, my profits decrease. So I kind of want any negation to happen in the link. So I kind of want the normal sense of direction to be positive. So here, if I get criticism, it increases my unhappiness. Well, that's just weird to say increases unhappiness. Instead, I could have said increased criticism decreases happiness. So the normal sense is positive. And that loads up so that the link makes the relationship a little more clear. I don't want to undo the link through a modifier on the word. All right, is there any questions about that? Is that pretty clear? And we'll get more practice with this. Okay. All right, so moving forward here, what do we got going into the weekend? So this was lecture B1. Tuesday will be B2. So there will be an opportunity to use Vensim if for those of you in class. Vensim is installed on all of these computers. So if you're in class, you can use Vensim on the computers. If not, then you can also have a laptop available. If you're at home, it will be useful to have Vensim. You don't necessarily have to have it during the class, but there will be an assignment coming up where you'll have to use Vensim. And if you really can't get Vensim, you'll have to use some other drawing tool to draw these causal loop diagrams. Do Sunday night on Canvas. Again, there's a muddiest point assignment. Then otherwise, before Thursday, that's when we'll have the Moorcroft reading on this. So that's the next reading assignment is on Thursday. So, and that's all that's labeled here. So that's all I've got for you today. So I'll give you the one attendance exercise, and I'll put the link in the chat. Oh. And the question I'll give you is there a how many negative links are in a negative feedback loop? And you can give me either an example number or you can give me a general property. And we'll end a few minutes early today. So those of you online, if you have any questions, I'll hang around, and you can feel free to drop off. If anybody has got any questions in class, I'm happy to take questions afterwards here. Otherwise, I hope you have a good weekend, and I'll see you next week. It looks like most people have dropped off online. So I'm probably going to go ahead and end the meeting and the recording, and we'll see everybody else on Tuesday. If you have any other questions, feel free to send an email.